except Ali. Okay. Next question. Okay. So in this question, these are just imaginary questions. Okay, I've made myself just to give you an idea how the questions are going to be. The actual questions we're going to do in why. So this question says that a radioactive sample initially has 240 counts. Okay, so it is having 240 counts initially. When 4,000 years have passed on, the count rate has dropped and it has now been reached to 30 counts. Okay, so we are supposed to find what is the half life, like how much time it would have been taken for it to decrease to one half. Okay, and like because we are having 4,000 years, so let us try to figure out how many times it has been halved. Okay, how many times it has been halved. So we can simply do this working. 240 is the initial one, and we have to go to 30. So 240 half is 120, 120 half is 60, 60 half is 30. So that means you're having one, two, and three half lives, isn't it? So each half life is going to be 4,000 divided by 3. Okay. Or I can make this question even more better if I just switch this to 15. So that's going to be one more half life. Okay. So four half lives. Okay. So 4,000, 4. And that's it. So for every half is going to take 1,000 years. Is that clear?
Yes.
Okay. But the questions sometimes are not this much simple. Sometimes background count has been given to you. Okay. Background count is the count rate which is present all the time, and that is not because of the sample. Okay. Now, what we are going to do? Just be with me. So, be with me. Whoever is writing, drop your pens, focus on the screen. This is something important, okay? This is the concept which you are going to use on the graph as well. This is the concept which you're going to use for any background radiation question. Please be with me, okay? Questions are sometimes challenging, okay? So I want you guys to do that questions in the class and after the class and come up with the queries, okay? So in this question, what they're telling is that, okay, my dear students, half-life is not applicable on background count, okay? Because background count is the one which is already present in the surrounding. It's not because of the radioactive sample. The only count rate because of the sample is going to get halved and halved and halved. So how are we going to do this? How are we going to do this? Okay. So now what exactly this is going to be something like this. Okay. So now what we are going to do, the first thing we are going to do is we are going to determine how many half-lives are there, like 48 hours and 24 hours. So number of half-lives are going to be, so we are going to do two half-lives. Okay. So we've got two half-lives. Now we have to find the count rate after 48 hours. Okay. The first thing we are going to do is subtract 900 and 100. So you're going to get 800. Okay. Now on this, you are going to apply the half-life thing. Okay. Two half-lives. So the first half-life is going to reduce to 400 and then it's going to reduce to 200. And then final count, you're going to add again that 100. Okay, because the counter does not know that it's the background radiation. Okay, so final count you'll add up again. So it's going to be 200 plus 100, so it's going to be 300 counts per second. Okay, so this was the concept. Please remember this. Step number one, subtract the background radiation. Step number two, apply the half-lives. Okay, find the number of half-lives and make it half, how many times it is. And then for the final count, you have to add that background count again into the reading. That's it. Understood?
Yes, sir.
Okay. Anything to be asked, you can. And then we may move into the questions. Simple lag raha hai, so it's going to be simple for you. Okay. So let's try to figure it out. इन्होंने अभी तक winter के papers ऐड ही नहीं किए यार. Have it there, winter papers. Because you know, practicing winter papers are getting messed up. Papa Cambridge? उस उस पे उस वक्त से है जब एग्जाम्स खत्म हुए थे, बहुत पुराने, इन्होंने अपलोड नहीं किए. मैं इसको यूज कर रहा होता हूँ. चलो ओके जी. A 3 marker. ठीक है. Look here. The first question is about the Rutherford atomic model. Okay. And the second question is about the half-life. Okay. So let's do it. The half-life of the isotope is 29 years. Okay. And the initial mass of the strontium is 25 micrograms. I want to find how much mass will be left after 87 years. So let us first find the number of half-lives. Okay. So I can just divide 87 by 29 to find the number of half-lives.
Sir, 3.
3 half-lives. Okay. So the amount remaining is going to be 1 over 2 to the power n times initial amount. Yes. The final answer must be in microgram as well. So no need to do any conversion. No. What is that?
Sir, 1.
It should be 3.1. How much you're getting? 3 point?
3.125.
3.125. 3.125. Okay. Now, this is the amount remaining. They are saying, question देखो. Calculate the mass of strontium that decays. They're not saying that how much is left, how much is gone. Okay. So 25 minus, let's consider this to be 3. Okay. Yeah. So what are we getting?
Sir, 21.875.
In 2SF, it's going to be 22 micrograms. Okay. That's the answer. Understood?
Yes, sir.
Okay, great. Physics is easy. To get good score in physics is not difficult. Believe me, you just need to practice your paper 2 and paper 6. That's it. Paper 4 is easy. And you have to, first of all, you have to like drop the scare of this, that papers are difficult. Inshallah, we'll be going into detailed past paper practice, okay? Once we cover the syllabus. So like all the past papers will be done in the class. You guys are going to solve with me. So like every paper has some challenging questions in it. Okay. So, okay, sodium and is converting into magnesium. Okay, you guys give a try. It's a beta decay and sodium is converted into magnesium. Okay, give a try, then we'll discuss. We did this yesterday.
Done, sir.
Mashallah. Okay, so what are your answers? Okay, so it's a beta decay. Okay, so we're going to start from sodium. Na2411 undergoing a beta decay in magnesium. The proton number does not change. Add 1 to the proton. Okay, and write. You're getting 3 marks for this. Just look at that. Yes, easy. The question above that is give 2 reasons why alpha emitters are not used as radioactive tracers inside the body. The first thing is that they have a very high ionizing power. Okay, they cannot travel long distances and they have a very high ionizing power. Okay. No penetrating power. Yeah, very high ionizing power. So you guys are. नहीं इसके अंदर जा सकती है मगर चली गई तो मसला कर देगी अगर आप बहुत करीब से उसको हिट करेंगे ना Okay, this is something okay. Suggest which radioactive emission, alpha, beta, or gamma, is suitable for detecting the leak in the water pipe. Like it should go, penetrate, and then go out. And then it's going to tell that there is a leakage. Yeah, sure. Okay, Amar is saying beta particles. And what's the reason? You guys, I want participants from all of you, please.
Sir, gamma.
अयान आंसर सोच के रखो ओके गैमा वाला भी एक बच्चा आ गया ठीक है और बीटा okay so there are mixed answers okay so you have to give the name and you have to support your answer Okay. Are you getting or not? Omar is right. Oh, exactly. So pipe. Exactly. Exactly. That's great. Nice. Mashallah. Shabash. This is the right answer. वो निकल जाएगा लीक से भी निकल जाएगा तो that won't make any difference. Very
अच्छा
good, Omar.
ठीक ठीक
शाबाश. अब्बू को I'll let your Baba know today. I'll let your Baba know today that your child is not studying in the class. That your child is not taking part in any of the discussion in the class. Okay. Yes. He is disturbing the class, and when I'm asking the questions, there are no response from his side. Okay. That's what I'm going to tell your Baba today. Okay, जी. Very good answer. Okay. Alpha particles, alpha घर से निकलते ही थक के वापस आ जाएगा. It cannot go. It can either it is going to be stopped by soil. Okay. It can't go. Number two, gamma rays are powerful. Okay, they're just going to escape. They're going to get transmitted. They're going to pass the leak as well as the pipe. Won't make any difference. Beta particles are going to be stopped by the pipe. But if there is a leakage, so they're going to pass away from it, like they're going to escape it. Okay, and they're going to get transmitted on the other side. So that's why the best choice is beta particles. Getting?
Sir,
Yes, sir.
I want to disagree with this.
Okay, what is your agreement?
I think
Let's go for that.
gamma, because this exact question came in my physics paper that I just had. I got the paper back
Uh-huh.
today and I have it in front of me, and I wrote gamma, and she marked it right.
Is she the i- is she the authority or okay? But the thing is that the MS is also like inclining towards gamma as well. MS ने जो है ना dual policy खेली हुई है, and MS is saying it could be beta or gamma both. Okay, but more supporting, yeah, okay. Just let me. Gamma is only the addition that will reach the detector through soil. Less gamma reaches detector through solid pipe. Okay, so this is but this is not the best one. Gamma would pass through intact pipe as well, cracked pipe, so no difference detected. Beta is stopped by intact pipe, so variation between pipe water and escape water can be detected. This should be beta, by the way. Zainab, what was your answer, by the way? What have you written for the explanation? Okay, you wrote emission should be
The
gamma, but
I
explanation.
wrote is so the explanation I wrote is because it is the most penetrating and least ionizing. Gamma can pass through easily anything unless it is stopped by lead blocks. And she gave me
Okay,
some marks
but
for
mera
that.
bacha, if it is going to, it might be that she must be drinking some tea or something, or she must be watching television by the time, and she's checking the paper. Just check with your other friend. Check with your other friend what she has. Because I've been a school teacher now. I know how the papers are checked.
Can't
I
you
know
just
that.
check the marking scheme for this specific paper to see the answer instead of like arguing though?
I do have my marking scheme in front of me. I have opened before telling you the answers. I have marking scheme in front of me. Okay, marking scheme is supporting both the answers, but more relative points are there for beta. Okay, so beta is an appropriate answer. Zainab, you can check with your other friends if they have written beta. It would have been the right answer as well. Okay.
Sir, हम सब ने same answer लिखा
सर
है.
नंबर तो मिल जाएंगे ना
But the thing is that you just think, yeah, think about this. Okay, yeah, physics is all logical. Just think about that. That if gamma rays are going to pass through the leak part and it's going to pass through the just like the intact part, so what is the difference it's going to make? How are you going to detect the leakage? Isn't it? It's going to pass by hook or crook by anyways. So how are you going to know that there is a leak or not? So beta is relatively a better competitor. So because beta is not going to pass, but if there is a leakage, it's going to pass and it's going to be counted on the other side. Okay. Next
Okay,
question says, why radioactive isotopes must not have a very short half-life? Because it is so short that it cannot be detected. Okay, it's just going to like as it escapes, as the sample is radioactivity and the excess radioactivity is going on, and it's going to just decrease and decrease and decrease, and it's going to get half. So we cannot detect. Okay, so the reason you're going to write the too short half-life is difficult to be detected. Okay. All right.
Yes, sir.
And we are basically explained why radioactive isotope must not have a very long half-life. So basically, this is a carried on question. Okay, this is a carried on question. So a very long half-life is that it's not going to, like, when radiations are going to emit, only then you are going to check the leakage. Exactly. So it's going to take so much long time, and the leakage is going to happen and happen and happen. Okay, so it's going to be harmful, or like the water under that pipe can be contaminated. So we want something which is going to uh, uh like in some minutes or seconds it can do, but not in microseconds or very small period of time. Okay, it can be hours as well. Okay, something which can be detected accurately. Okay, so that is the thing. Is this clear? Okay. So they're saying the background radiation is 26 counts per minute and the counter is showing 382. So what is the count rate because of the source? So we have to subtract the two count rates. Arey bhai, the counter is showing a count rate and the background count is this. They're asking us to find the count rate because of the source. Yes. Okay.
Sir, 356.
All right. Good. Explain what is meant by nuclear fission. I've taught you guys, so you can just do it. Okay. And we have to write down the nuclide equation. Okay. Nuclide equation, isotope deuterium, one proton, one neutron. When two nucleon of deuterium combine a hydrogen and neutron form, you have to write this. Okay. So 3 mark. Let me write down this for you. No. It's nuclear fusion. 2H1 plus 2H1 is going to form 4He2. Okay. And a neutron are formed. Helium. Okay. And a neutron. But over here, it's not like conserved. And a neutron is formed. Yeah. Okay. So neutron is formed. That's it. Good. That's good. Fine. This is going to be the equation. All right. एक न्यूट्रॉन रिलीज हो गया, न्यूट्रॉन बाहर निकले, वो कहते हैं हीलियम बना है. मुझे लग रहा है कि इट शुड बी 3H1. जस्ट लेट मी चेक द मार्किंग स्कीम. वेट 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 वेट. Two deuterium atoms are combining together, 2H1, 2H1. Okay, so that's going to form 4He2. Okay. Oh yes. Okay. All right. So it's not going to be okay. Just okay. 2H1, 2H1 going to form helium. No, it's not 4H2. It's 3He2. And one neutron is formed. So 1 and 0, like this. This is the isotope of helium. Okay, so that's the thing. Exactly. Okay, please note down this. Okay, note down this equation in your notebook. This is deuterium. Okay, deuterium and isotope of helium. Done. Can you move on? Let's go.
Yes.
I need to go for those questions. Yeah, जिसमें वो आते हैं ना. Summer 23 भी देखना है. Summer 23 is not there in the past papers. Graph वाला question देखना मुझे. Physics math tutor पे you just need to go and look out over there. You'll find the questions, the graph ones. I think so. They are in some old papers. This is easy, okay? Quite easy. Describe how thermal energy from nuclear reaction is used to generate electricity in a power station. So we have already discussed about that. Okay. The nuclear energy is basically because of the nuclear fission, energy is released, and that energy in turns is used to because there is heat energy. Okay. So it's used to what it does is going to convert that thermal energy into the kinetic energy of the turbine, which in turns is going to convert into electrical energy. सबसे पहले ये होगा कि the first step is going to be nuclear fission. Okay, because of fission, energy is released. Okay, that's going to be the first point. Because of fission, yeah, energy is going to release. It's going to be basically nuclear fission, and nuclear energy is going to be released, which is going to get converted into thermal energy. Okay, that thermal energy basically makes a steam. Steam turns the turbine. Turbine makes, okay, for every time basically, yeah, every time turbine is rotated because of steam. Okay. O levels के papers है ना, उसके अंदर we can find that graph questions. So I'm just going into the O level papers as well, a few of them. Okay, this is alpha decay, 3 mark. Omar, यकीन आ गया? यकीन नहीं आ रहा था कल. Okay, just look at that. Everything. So these are doables. These are not that much difficult. Okay, you'll be able to solve that. So they have given you some cases, okay, and they're like, okay, this is important, that what should be the half-life. This is important. Like you're just going to predict the half-life as well. When it's going to half, emissions are going to get outside, okay? So then you can predict the count rate. Okay, so starting from like one by one, जरा part कर लो यार. एक बच्चा एक बताओ, ठीक है? एक बच्चा type of radioactive emission, the other one explanation, the other one try to think about a half-life. Class participation is very important. I can just see that most of the students are not participating for some reason. This is your class. Okay, when you speak, you'll come up with the ideas, and then you're going to grow up. Okay, just speak out. Don't be quiet. Okay. Yes, the first one, Ziad.
Okay. For each application of radioactive isotopes, you can explain. Okay. Household smoke alarm, that should be alpha.
Alpha, good. And
I don't actually know why it's alpha radiation, to be honest.
okay, you weren't there in the class yesterday. We talked about the smoke detector. Smoke detector is basically because alpha particles have the highest ionizing power. Alpha particles are going to ionize the smoke particles. Those ions can be detected and they can give an alarm, okay, so that you may know that there is smoke over there. Okay. So no, if half-life is very short, so it's going to finish up very quickly, isn't it? The half-life, like every time is getting half, it's going to go away. Is it a smoke all the time? Is it a smoke all the time? Okay, so you can consider that to be in airs. Okay, airs, some airs.
So
It
the
stays
first
there.
alpha. Sir, the first के लिए
First is
alpha.
G alpha लिखना पड़ेगा. It's alpha.
ठीक है sir.
And the reason is very ionizing power. very high ionizing power. Okay, and half-life is going to be like in years, like you can write any like 10 years, 5 years, something like that. Okay, because it is continuously emitting the radiation. Okay, but you don't want it to be finished very quickly, so you can just leave it over there. Second one is
Beta.
measuring. Okay,
Particles.
yeah, have you ever tried beta particles? Okay, an explanation. Zainab, you should give the explanation.
Because it can partially penetrate aluminium.
Very good. It's going to get stopped by aluminum, so we can detect it. Okay, very good. All right. So absorption depends on the thickness of aluminum. How much it is absorbed. If it is absorbed so much, that means the aluminum was thick. A little extent of absorption, that means the foil was thin. Okay. And the half-life, the marking scheme says any number. Any number. Okay, so you can consider any
सर
number.
पार्ट 1 की
Years.
हाफ लाइफ कितनी थी?
पार्ट 1 की हाफ लाइफ इन्होंने बताई है 10 से लेकर 100 इयर्स के बीच में कुछ भी लिख दो, because you don't want it to be replaced over and over again. ठीक है, तो
Sir,
sensible half life ये है कि you just want it
हमारे
to be
को
there
कैसे
and it
हमारे
gets
को
out and out. जी,
हमारे को कैसे पता होगा कि हाफ लाइफ जैसे कितना होगा?
पता चलेगा. हाफ लाइफ जो है ना वो बहुत छोटी नहीं रखते हम, यानी कि मंथ्स में नहीं रखते, डेज में नहीं रखते, because you when you have put something you just want it to be there. Okay, and it is continuously emitting the radiations. Okay, so half life is basically it's going to reduce to half. Okay, for instance, you have bought a car. Okay, and you want the car to be there with you for some time. All right, so you are going to buy a car which will give you this amount near to the purchasing amount for some 10 years or 5 years or so, isn't it? So इसी तरह से हमने जो sample choose करना है alpha का, so it's going to be there like 5-10 years and so on, but not very big. Okay,
ठीक है.
and neither very short. Okay, now this thing explained why lead is radioactive. देखो भाई, for a radioactive sample, the nucleon number should be very big. Okay, so you can see it's 214. Okay, so it is having too many neutrons and unstable. Okay, so it's going to decay and give away the neutrons by either alpha or beta decay. Okay, understood? All clear?
So it needs to go under radioactive decay to be able to be stable, right?
Can you repeat please? कुछ जिंदा विंदा रहने की बात की है इसने, हाँ बताओ.
सर आपने बताया कि लीड 214 रेडियोएक्टिव अनस्टेबल होता है, तो मतलब जैसे इट अंडरगोज रेडियोएक्टिव डीके टू अचीव अ मोर स्टेबल स्टेट, राइट?
इधर आप, हाँ हाँ बताओ. हाँ बारी. Exactly. What is the other way it can be stable? It's too heavy. So to become either the atoms are either the atoms are so lighter so they'll mix up, or the atoms are so heavy so they split up. ठीक है, to become stable. क्योंकि उन्होंने 1-2 दिन नहीं रहना होना, उन्हें रहना होता है, बहुत सारा रहना होता है. ठीक है, so they have to stay. So they want to become stable. Okay. Smoke detector. Okay. And you can see here alpha decay and this. I just want to go into the background and into the half-life questions, to be honest. Okay, so that's why I'm looking into it.
Sir,
I'll share the physics.
November 2022 में एक ग्राफ को क्वेश्चन है.
Okay, that's great. This is what I wanted from you to see. Okay. Any of my students who has got their physical past papers, they can just let me know. Okay. Okay, this is another one. Then you 2015. Okay. So Habiba beta, आपका कौन सा वाला है? O levels में ना?
हाँ,
O levels.
पेपर 22 है.
Paper 22. And the year is
November
कौन सा?
2022.
2022, winter 22.
हाँ.
ठीक है. Guys, please solve the O-level papers. They are more challenging, to be honest. Oh, yes, yes,
हाँ
yes.
this one.
Determine the half-life. Okay, that's great. Okay. Okay. We have to find the half-life. Sallallahu alaihi wasallam. Is there a background count? Yes, there is. There is background count. So we have to. This is the background count. Okay. How much is that going to be? It's 3. It's 3, I guess. Okay, this is 10. Okay, 4, 6, 8. It's midway 3. So background count is 3. Okay. Your initial count rate is 60. Okay. 60 minus 3 is how much? 57. Okay. 57 divided by 2 is how much?
28.5. 28.5.
28.5 हो गया. दोबारा 3 ऐड करो. So it's going to be almost
31.5.
31.5. Now you have to go into the graph and cut the graph. Okay, this is 31.5 somewhere over here. Okay. And you're just going to come down all the way over here. Okay. So it's almost okay. So because this is 60. So each one is representing how much? There are 10 boxes and it's representing 20. So each box is representing 2. Okay. 42, 46, 42, 44, 46, 48. No. 10 boxes representing 20. No. There are 10 boxes representing 20. So how much is each box representing? No, yaar. There are 10 boxes representing 20. Okay. So one box is 20 over 10. It's 2. No. It's 40. Oh, my bad. It's not 20. It's 40. 40 to 80. Yeah. So it's 4. Okay. So 44. Yeah. 44, 48, 52. And it's somewhere like 53. Or you can take 54 as well. So this is the half-life. Okay. Understood? Okay, ji. So 10-minute break for namaz and we'll do it after that. Because radioactivity is a random process. So it's not always in the curve. Okay, it can occur like it has no fixed pattern. Okay.
Sir,
We'll
spontaneously
continue
comes
after
away.
namaz. Achanak. Koi regular pattern now.
Okay.
Prayer break. We'll meet after it.